My name is Dyon Kreffer. I'm from the Brabant University of Applied Sciences Games program. And for my Bachelor graduation project, I work with the research and development team on the creation of digital humans. Brabant University of Applied Science is working on the VIBE project, with the goal of developing a realistic digital human for training purposes. To develop highly digital humans, we use a process called photogrammetry, by taking multiple synchronized photos of a person and then creating a 3D model that can be animated. One of the difficulties of using this method is the inability to correctly recognize and process small surfaces or filaments. That is why, in most such systems, actors use a hair cap during the capturing phase to avoid deformation, and afterwards a 3D artist must manually build a 3D hair model. For this project, it was requested that I investigate how we can use deep learning to support reconstruction of realistic hair features and incorporate it into the after production pipeline to reduce the work required to manually build 3D hair models. During my initial research, I found the 2018 paper 3D hair synthesis using volumetric variational autoencoders, outlining the workflow of 3D hair creation. I followed their approach, adapted, and experimented myself, which led to my current progress. We start with a variety of datasets of images and different hairstyles that were annotated by me and their 3D representations. This included a flow field for hair directional information and an occupancy field for hair density information. We take all our 3D hair representations and use them to train a variational autoencoder to be able to recreate the different hair representations we have collected. Variational autoencoders are a generative deep learning architecture that is composed of two parts: an encoder that is able to digest a complex dataset into a set of variables, and a decoder that can take those variables and reproduce the original data. In parallel, we developed a deep neural network which was able to predict a hairstyle based on a given image. For that, we use a known algorithm known as ResNet50. ResNet stands for Residual Neural Network, and they allow some layers to be skipped, like shortcuts, which effectively simplifies the network and improves the learning process. Those results are fed into an iterative error feedback algorithm that helps the system to iterate the outputs to improve predictions. With both systems trained, we use a statistical method of dimension reduction, namely principal component analysis, to be able to link the output of the image directly into the decoder section of the autoencoder. This way, we can feed an image to the hair prediction system, and the decoder is able to generate a 3D hair representation of a hair model. Those representations are then passed to a 3D modeling software called Autodesk Maya, and based on the density field and the flow field, we can grow hair guides, also known as strands, from a modeled scalp, and replicate with a high level of accuracy the hairstyle of the original photo. By using a 3D modeling software as a platform to grow from, we're able to use the existing toolset for editing and customizing the hair model even further and use it for any related purpose. In our case, to export it to a game engine called Unreal Engine, which recently released a new experimental system for hair. Such system is fully integrated with the photogrammetry studio, allowing the automatic generation of the hair to be developed without human intervention, but still allowing 3D artists to refine the model as they would prefer. In addition, this allows for quick iteration over several hairstyles of the same character.